looking at the event A or B. And from yesterday, we talked about this as A union B. On a Venn diagram, this is all of the possible space, both in set A and in set B. So it could be either only A, only B, or both. So the first thing we're going to see is the chance of drawing a black card and the chance of drawing a red card. So the probability of S is the chance of drawing a spade. So there's 4 suits, only one of them is spades. The probability is 1 in 4. And the chance of drawing a red card is equally easy to calculate. There's half red cards, half black cards. So we have a 50-50 chance of drawing a red card. This is just a single event. The probability of drawing a red card or a black card means we can either get a spade or a red card, or both at the same time, which is what's the chance that I get a red card or a spade? 3/4. That's correct. Now what's the chance that I pull out one card and it's both a spade and a red card at the same time? 0. There's no spades that are red. So actually there's a mathematical way that we can calculate or just using P of R and P of S. So there's a simple relationship between the value for OR and the value for S and R. We just add together the probability of S and the probability of R. Then we get the probability that either one happens. Yes, Carl? You're right. Last time we saw we had to subtract the intersection. And what is the intersection in this case? 0. So technically we should subtract the intersection. But this time we don't have to subtract the intersection because these events are mutually exclusive. And what mutually exclusive means is that on a Venn diagram, they're just 2 separate circles. They have no overlap. So as it says here, mutually exclusive events have no common outcomes. For mutually exclusive events, the intersection is 0. So this formula works only when the events are mutually exclusive. So what about when the events do have common outcomes? Like drawing a face card and drawing a spade. The chance of drawing a spade is the same as what it was above, 1 in 4. Now a face card means a jack, a queen, or a king. And since there's 4 suits, we've got 3 cards times 4, so there's 12 possibilities out of 52. And actually, I'm going to just write these ones over 52, just so that we have a common denominator to compare the answers. Now, the chance that you get a spade or a face card means that we're going to count all the cards that are spades, face cards, or both spades and face cards. So we have 13 spades, And then we've got all the red Jack, Queen, Kings, plus the Jack, Queen, King of clubs. So altogether, we only have 9 more cards. We don't actually have 12 more face cards because we already counted 3 of them. 3 of them are also spades. So altogether, we've got 13 plus 9, or 22 cards that are either face cards or spades or both. Okay, so it's not like the example above. We can't just add 13 plus 12 and get 25, because there's some cards that they have in common. This time the intersection is not 0. So P of S and F means we're counting all the cards that are both a face card and a spade, like the Jack of Spades, the Queen of Spades, and the King of Spades. All these cards are both spades and face cards. So there's a 3 out of 52 chance that we get S intersect F. So this time the formula is a little bit different. The probability of getting S or F is the probability of S plus the probability of F. But if we just add those two together, we're going to count some of the cards twice. Just like we saw last time, we have to subtract all the ones that they have in common. And this is the most general form for finding the value of P of S or F. Okay, so remember that on a Venn diagram, P of S or F means this area here. So in order to find that area, we're going to add P of S and P of F. But when we do that, we've counted the middle part 2 times. So that's why we're going to minus just the middle part. And this is 2 events that are not mutually exclusive. They have an event in common. They have some common outcomes. So they do have some overlap. So we have to take that into account. Are there any questions? Okay, let's apply it in a practice situation. Okay, so let's say you've got 18 players on a hockey team and 10 of the players are forwards and 5 are willing to play in goal. So we're going to make 1 circle for the forwards, 1 circle for the people in goal. And of these team members, 2 can play forward and are willing to play in goal. We want to find the probability that a player is a forward or is willing to play in goal. Now, quite often what I see my students doing is they'll say, okay, there's 10 forwards and there's 5 in goal. But this is not correct because there might be some people in the middle. And the F circle means that everything in this left-hand circle has to add up to 10, including the stuff in the middle. So always put your value in the middle first. And then that's right here. 2 can play in forward and are willing to play in goal. So 2 is what they have in common. So that would mean right now that I actually have 10 forward or 12 forwards. I don't want 12 forwards. Those numbers are wrong. I have 8 forward, 8 that are only forwards. So now all together in the forward circle, I have 10. So I have 2 that are willing to play forward and play in goal. I need 5 all together in the goal circle. So I have 3 that are only able to be goalies. So now my defense, all the other players, would be whatever I have left over. I have 13 players altogether that are either forwards or goalies or both. So since my total is 18, that means I've got 5 people left over that are probably defense or some other role on the soccer team, hockey team. So now the question is, what is the probability that a person is a forward or willing to play in goal? That's all the people in either of the circles, which would be 13 out of the total 18. So quite often these problems are very nice to solve with a Venn diagram. We can also apply the formula on the previous page. The probability of forward or goalie is the probability that they're a forward and the probability that they're a goalie minus the probability that they're both a forward and a goalie. So we have 10 out of 18 forwards. We have 5 out of 18 goalies. And we've got 2 that can be both. Ten plus 5 minus 2 is also 13 out of 18. So that's how the formula translates into the Venn diagram and vice versa. And example 2 is also very typical of the sort of problem you might see even on a IB exam question. And whenever you see these percentages, it's really nice to do with a Venn diagram, especially when there's only 2 possibilities. In this case, you can be either taking mathematics or chemistry. So we can make a math circle and a chemistry circle. Again, you want to fill in that intersection first. If you know how many take both, that can go into the Venn diagram first. So 50% take both math and chemistry. We've got 60% chemistry, so that means that all together in the chemistry circle we need the total to be 60. Which means that you have exactly 10% that are taking only chemistry. We know 85% are taking math, so we want 85 to be total in the math circle. So if we subtract the intersection, then we are left with how many percentage are taking only mathematics. So now we've got some more interesting questions here. What's the chance that a selected student in grade 12 takes math but not chemistry? So that means only math. We've got 35%. And if you want to write that in set notation, that would be taking math and not chemistry. For part B, we want to know what's the chance that they take neither math nor chemistry. So that means everything on the outside. We've got to figure out how many people are left over. So that'll be all the people, 100%, minus the ones on the inside, the 35%, the 50%, and the 10%. So that would be 100 minus 95. So there's only 5% left that are taking neither math nor chemistry. And if you want to write that in set notation, you could say not math and not chemistry. The complement of math and the complement of chemistry. Are there any questions? Okay, we can turn over to section, it should be 6.4, where we have the event A intersects B. Also known as the event A and B. So that's this part of the Venn diagram. With this section, we're going to look at the possibility of having more than one event. So it could be two separate events. Sometimes, if you're doing two trials, the first trial has an effect on the second trial. So sometimes what we're going to need to look at is a conditional probability. Sometimes the probability of one event happening is changed if you know some information about the first event. So this notation here, the probability of B given A, means the probability that event B occurs if you know that event A has already happened. And this mostly happens with two trial events. So the typical example is pulling cards from a deck without putting them back again. I'm going to draw two cards. P of A is the chance that the first card that I get is a spade. What is that probability? 1 in 4. It's the same as what we did before. Very good. 1 in 4. I pull a card. And I'm putting that card aside. Now what's the chance that I get a spade? I only have 51 cards left. So it's something out of 51. So there's 12 spades left. How do you know that there's 12 spades left? Is this card a spade? So the problem with the second event, the problem with B, is that you don't know if the first card was a spade or not. Okay, so you can't actually find the probability of B happening unless you know what happened with A. So the chance that the second card is a spade depends on what happened to the first card. If the first card was a spade, then you'd only have 12 spades left. But if the first card was not a spade, then you'd still have 13 spades left. So it might be 12 out of 51, it might be 13 out of 51. So that's why you have this notation here. P of B given A means that you already know that the first card was a spade. So that means you're given that A happened. if we know the first card was a spade, then we know that there's only 12 cards left out of the 51. But if A was not a spade, then we would still have 13 spades left. So the probability that B happens depends on what happened with A, whether A was a spade or whether A was not a spade. And I think on your paper it's written as the probability of A intersect B, which is the same as A and B. So now we want to find out what's the chance that the first card's a spade and the second card's a spade. And this is really nice to do with a tree diagram, because we only have 2 trials, so the tree's not going to get too big. So we'll make a tree. There's 2 possibilities for the first card, and then there's 2 possibilities for the second card. So the first card could either be a spade or not, meaning a club or a diamond or a heart. The second card could either be a spade or not. And then with your probability tree, what you can do is you can write the probabilities on each branch. So the chance that the first card was a spade was 1 in 4. And the chance that the first card was not a spade is exactly the opposite, 3 out of 4. Those numbers will add up to 1. Now, because we're not replacing the card, that means that we only have 51 cards left in the deck. So if the first card was a spade, the chance of getting another spade is 12 out of 51. There's only 12 spades left. If we get a spade at first, then the chance that we don't get a spade, 39 out of 51, we have to count up how many non-spades there are. There's 39 other cards. Okay, if the first card was not a spade, then the chance that the next card is a spade, well, we still have all the spades left, so it's 13 out of 51. And if the first card was not a spade, that means we've taken out one of the 39 cards, so we have only 38 non-spades left. So that's a tree with different probabilities on it. So if we want a spade and a spade, A and B, that means we want this first card to be a spade and the second card to be a spade. We want this branch of the tree. Okay, whenever you're trying to calculate the intersection between 2 independent probabilities, you can multiply their values. So the total probability that we get a spade and then another spade is just 1 out of 4 times 12 out of 51. And we can cancel and simplify this to 1 out of 17. And now you can see the relationship between what we did here and what we did up here. 1 out of 4 is just the probability of A. 12 out of 51 is the probability of B if we know that A happened. So in order to find the intersection, we can take the probability of A times the probability of B, given that A already happened. Okay, so 1 over 4 is the chance that you get a spade. And 12 out of 51 is the chance that you get a spade if we know the first card is also a spade. Yes? Because these two events are independent. No, that doesn't really explain it very well. These two events are actually dependent. The first event depends on, the second event depends on the first event. If the first event was a spade, then it'll change the probability for the second event. Basically, the probabilities, you have two choices. You can either add the probabilities or multiply the probabilities. So you're going to add the probabilities when you want to find out the chance that it is either A or B, when you're trying to find out the total altogether. Generally, you're going to multiply the probabilities when you're trying to find out A and B happening. Just like we did yesterday with the trying to find out the total sample space for the dice. We looked at the 4 possibilities for the red dice and the 4 possibilities for the green dice. So you had a 1 in 4 chance and a 1 in 4 chance. We multiply those probabilities. It's a little bit easier if you don't have replacement. The square? We'll leave that one. You can put in the total probabilities if you want to. So the chance that you get a 13 of spades, or sorry, the chance that you get a spade at first, and then another spade, or the chance that you get one of the other cards first, and then a spade, or the chance that you get another card, and then another card that's not a spade, and the chance that you get a spade, and then another card. These are all the 4 possibilities. These are all the 4 branches of the tree. And all those things should add up to 1. Okay, so that would be using the sample space to be able to come up with a solution. But don't worry too much about that. And the most important thing that you could get from here is the formula for finding the intersection with the conditional probability. So these 2 events here are called dependent events. The outcome depends on the first event. Now if I have a deck of cards and I pull out a spade, and then I replace it back again, what's the chance that I pull out a spade? Same chance. But the outcome isn't affected by the fact that I put the card, the fact that I got a spade at first or not. So the chance that I get a spade at first is 13 out of 52. The chance that I get a spade the second time is still 13 out of 52 because I put the card back again. And this probability doesn't depend on what happened with A. If A didn't happen, or A did happen, Doesn't matter. Still have a 13 out of 52 chance. So again, if we make a tree out of this, the two possibilities are that you get a spade or not a spade. With a tree diagram, you never want to draw like more than two possibilities for each branch. You wouldn't want to draw a branch for like spade, diamond, heart, club. Your tree would get really big really fast. So that's why we make it easier by looking at just the two possibilities. Hopefully you'll be able to break down every probability into an either or case anytime that you need to draw a tree. Okay, so the first branch represents the first card, and the second branch represents the second card. So again, we want to know the chance that we get a spade on the first card and a spade on the second card. So really we only need to write down the probabilities for this branch of the tree. So what's the chance you get a spade the first time? 13 out of 52, or 1 in 4. And we put the card back, so the chance that we get a spade again is still the same. So just like throwing two coins, to find the chance that we get both a spade the first time and a spade the second time is 1 out of 4 chance times 1 out of 4 chance. And if you develop this into a formula, this is the probability that the first one happened times the probability that the second one happened, given that you know that the first one was a spade. And because these two events don't depend on one another, P of B given A is P of B. It doesn't actually matter if A happened or A didn't happen. That probability doesn't change because we put the card back. So this works for independent events. Independent events means that the second event does not affect the outcome of the first event does not affect the outcome of the second event. And we won't do this with the sample space because I think that might just make it more confusing than it has to be. Yeah, on the back side you have a summary of these two results. Okay, and two very important pieces of vocabulary. If A affects B, then A and B are dependent. If A does not affect B, then A and B are independent. And the most common example of dependent events is cards without replacement, when you don't replace the card before you pick out a second card. Okay, so we'll go over a few examples, and then you'll have a chance to practice. Yeah, he's at a soccer game. So whenever you have a probability question, read carefully for these words. If you see the words without replacement, then you know that it's pointing you towards something that's dependent. And then you're going to have to use this conditional probability. Then probably B is going to depend on A. So let's think. Out of a deck of cards, which numbers are prime? Two, 5, 7, 3. And we won't assign numerical values to Jack, Queen, and King. The number 1 is not prime. The number 1 only has one factor, and every prime has 2 factors. So we only actually have those 4 prime numbers. So let's find the probability that we get a prime number the first draw, and then we get a prime number again the second draw. Yes, correct. 1 is not a prime number. A prime number has exactly 2 factors. Exactly 2. And prime, the number 1 only has 1 factor. So from the formula above, the chance that we get A and B is the chance that we get A times the chance that we get B. But because we're not replacing the cards, B depends on A. So we write the chance that we get B if we know that we got a prime number the first time. So let's see, I've got the numbers 2, 3, 5, and 7. So I've got 4 different numbers. And then I have 4 suits. So altogether I've got 16 prime cards in the whole deck. I pull out a card, throw one away. For the second try, I only have 51 cards left. How many of them are prime? 15, because I took out 1. Okay, because I know that event A happened. So I want to know what's the chance that I get a prime and then a prime. So I got a prime the first time, took it out. Now I only have 15 primes left out of the whole deck. And then we can calculate that probability. And you could write that as a fraction in simplest form, or you could write it as a decimal. So I've got a 9% chance of getting 2 primes. I think on your paper I wrote this as A naught and B. A complement and B. Which means that's the chance that the first one's not a prime, and the chance that the second one is a prime, given that the first one wasn't. So if I have 16 primes, then I have 52 minus 16, or 36 not primes. So I've got 36 cards that are not prime. So 36 out of 52 chance of getting a not prime. And then if the first card was not a prime, now I've only got 51 cards left. How many primes do I have left for the second try? I still have all of them in there. So 16. And that's it. 36 times 16 divided by 52 times 51 gives me a 22% chance. Much higher probability. Any questions? One last example. Two more examples. So I've got two boxes. Very common box and ball problem. I'm going to go and pull out a ball from the first box, put it out here, and pull out a ball from the second, that's a foot, box, and put it here. And I want to know what's the chance that both those balls are white. So I want to know what's the probability that I get a white ball and a white ball. So what's the chance that this first ball from the first box is white? Four out of 6. You count the white balls. So I've got 4 white balls, and I've got 6 balls altogether. Got it. Now I look at the second box. What's the chance that I get a white ball from this box? I've got 2 white balls out of 5 altogether. It's getting easier again, right? So 2 times 4 is 8 out of 30, or 4 out of 15. And if you wanted, you could change this to a percentage. 27%. So the question is, are these two events dependent or independent? Independent. The reason why is because it doesn't matter whether I choose a green ball or a white ball from the first box. There's still the same number of green and white balls in the second box. Sometimes you get really hard questions where they like take the ball from this box and then they put it into the second box. And then they take one out of the second box. That makes it dependent. But in this case, and there goes my foot, it's independent events. So it's much simpler to calculate. And the last one is if we throw a coin 3 times, what's the chance that we get at least 1 head? Now, if you throw a coin, does that affect the chance of getting heads or tails the second time? No. This is independent events again. And whenever you see the words at least 1 in probability, it's very helpful to think of the complement. The complement is the opposite. The probability that we get at least 1 head is 1 minus the probability that we have no heads. Okay, the opposite of at least 1 is none. So that would be 1 minus the chance that we get tails, tails, tails. The chance that we get tails, whoa. The chance that we get tails the first time is 1 out of 2. The second time, the probability doesn't change. And on the third throw, the probability is still the same. So this is 1 minus 1/8, or 7 out of 8 chance. And you could also figure this out by making a tree and looking at all the possibilities. So your homework for the weekend is to finish a worksheet. And I hope that you can finish at least one page in class today.